And if you wouldn't mind releasing your screen.
All right.
Very good. And let me introduce our second speaker. Our second speaker comes from Camus, if I recall. Texas A&M. Patrick, are you there?
Yes, sir. Can y'all hear me?
We hear you fine. You're going to talk on identifying source attributes of spoofed plutonium samples using isotopic ratios, correct?
Yes, sir.
All right, the floor is yours. You've got 20 minutes, and then I'm going to cut you off mercilessly.
Mercilessly. All right, then I got to be on my game. Let me get this slideshow going. Can everybody see it okay?
Yep, we see
Awesome.
it fine. Don't forget to use your pointer.
Oh, yes, of course. So thank you for the introduction. My name is Patrick O'Neill. I'm a PhD student out at Texas A&M, and I work with Dr. Chirioth. And today I'm very excited for the opportunity to share some work we've been doing, identifying the source attributes of spoofed plutonium samples using isotopic ratios. So kind of an introduction, some previous students at Texas A&M were able to develop a nuclear forensics methodology to identify certain attributes of separated plutonium samples, which include reactor of origin, the burnup, and the time since irradiation. Unfortunately, this model is not robust enough to handle what we are calling spoofed plutonium samples, which are samples that contain plutonium from maybe multiple different reactors, or they could be from the same reactor but come from multiple different batches with different burnups and different times since irradiation. So my work has been trying to develop ways that we could increase the capability of this methodology to handle those cases. And so why is this relevant to MTV? So if you look at the NNSA mission statement, the NNSA is working globally to prevent state and non-state actors from developing nuclear weapons or acquiring weapons usable material. And attribution is something that can potentially deter state support of nuclear terrorism, because if the global community is able to interdict a plutonium sample and able to figure out a country of origin, then obviously there would be consequences for that country or that facility. So it reduces the likelihood of just a blatant state handoff to a nuclear terrorism group. And it also encourages countries to ensure that there are no security lapses, which would lead to non-state actors procuring special nuclear material. So that's why we're doing this. Just some background on the methodology that's been developed, the steps that were taken to develop this forensic methodology. The first step was creating a database of plutonium and fission product isotopics using high fidelity MCMP models of various different reactors. And then from that, the students who did this before me, they selected relevant intra-isotope ratios to help resolve the 3 parameters of interest that we talked about already. And then a code was developed to perform maximum likelihood analysis. And then also some validation experiments were done where we irradiated some samples of uranium to produce plutonium, and then there was, separations, destructive assay, non-destructive assay, and we were able to use the data from those test points and put them in our model and see, is it able to actually resolve those parameters of interest? And it works. It works for pure plutonium samples. Or when I say pure, I mean like samples that are not spoofed. So samples with a single reactor of origin, burnup, and time since radiation. So this is just to help kind of visualize all of the different things that go into this methodology. We have all these different reactor types, and then for each reactor type, we generate a matrix of burnup and time since radiation for all of these ratios. So this is quickly evolving from a nuclear engineering problem to a statistical analysis problem, and how do you handle the data, and with that many data points at your disposal, what is the best way to meaningfully gain conclusions? So a visualization of this problem, on the left side of the screen, we have a pressurized heavy water reactor likelihood surface for a pure PHWR plutonium sample at 1 gigawatt day burnup and a year of time-sense radiation. And we can see that in the likelihood surface that the methodology is accurately predicting where the plutonium was produced, as well as when it was produced and how long it was in the reactor. So that's very encouraging for us. But then if we look on the right side of the screen, here are two likelihood surfaces that were generated for a sample that was 50% pressurized heavy water sample and 50% AP1000 sample. And as you can see, it doesn't quite predict both of them at 50%. It over predicts the AP1000 at a likelihood of 10 to the 11th versus a likelihood of almost 8. And it also does not accurately predict the time-sense radiation or the burnup, with the methodology predicting a burnup of 0 in the PHWR and no time-sense irradiation, and over predicting the burnup and the decay time for the AP1000. So delving into that a little further, you can see some plots that depict how our parameters that we want to resolve, how they are, the predictions change based on the fuel composition. So this is varying from, again, that PHWR and AP1000 fuel mixture, and trying different percentages of each. And as we increase, so these graphs are as we increase PHWR fuel percentage, you can see how our prediction on our three parameters change. Basically, we never get an accurate prediction of burnup or time-sense radiation unless it's a pure sample. And then also we can see that the AP1000 is over predicted until the sample is over 75% PHWR. So this is a problem, right? And it for the methodology to continue to have value, it's something that needs to be addressed. So some of the underlying principles of the methodology that can help shed some light on this is looking at our intra-element isotope ratios and seeing what they resolve, and then seeing how they are put together. In the current methodology, for log likelihood, it's additive. You find the likelihood that your measurement matches up with each measurement in that ratio, in that big matrix, and then for each of the 10 ratios, you add the log likelihood, or you multiply their just regular likelihood together. So while we know what each of these intra-isotope ratios helps resolve, we don't really use that in our methodology, right? We kind of just all throw it together into one pot. And so one of the approaches that myself and Dr. Chirioff have been working on is, what if we actually use these intra-isotope ratios in a more, I guess, in a smarter fashion, actually use them for what we know they can do. And so what we are seeking to do is basically grouping these into kind of groups that resolve specific parameters, create initial guesses, and then let them work together to get us more accurate results. So we've done this for one parameter so far, which is reactor discrimination, I think probably our most important parameter. And so this is a visualization in 3D space, how our two samarium isotope ratios and our Pu240 to Pu239 ratio interact. And as you can see on the right in the 3D space, there's separation between these curves, which is what we really wanted, because something that presents a problem is if you have an isotope ratio that can be both two different reactors. So for this, we're comparing the PHWR, the AP1000, and the fast breeder reactor, FBR. And then on the left, you can see the projections on each plane for each of the different isotope ratios. And it's color mapped to burnup. So we can see how these ratios change with different burnup using the color mapping. So just to further emphasize the point of how separate those curves are, these are our probability distributions for a sample from each reactor that's at 1 gigawatt day per MTU and a time since radiation of 365 days. And as you can see in the summariums, we have a really good separation between these probability distributions, which makes it unlikely that we would confuse the three reactors. In the plutonium, there is obviously overlap with the AP1000 and the FBR, but we're okay with that because the FBR in most of the other ratios is very different from the AP1000 and the PHWR. So our difficult thing to resolve is a difference between AP1000 and PHWR. So we're okay with that. And basically, want to use these different groupings to do is we can perform the reactor discrimination with this group of isotopes and then maybe perform the burnup resolution with another group of isotopes and basically be creating initial guesses that we check with the other isotope groupings. So in conclusion, I think there's a lot of promise in this avenue of improving the methodology, and we're excited to start kind of developing a flow structure for our data where we're actually using it in a more meaningful way. So the expected impact of this is that we can provide another tool in the toolbox for those who monitor foreign nuclear fuel cycles. This can be used, when you interdict plutonium. It can be used if you were just able to sample somebody's plutonium, although that's not something that typically happens. And it could also be used in environmental sampling analysis. Our validation experiments, we had very little amounts of plutonium that were generated, and we were able to use that. So a little can go a long way in this type of analysis. So as far as the impact that MTV has had on this project, we have 2 collaborations going right now. I am working with Dr. Chi Cheng at Lawrence Livermore National Lab. We're utilizing machine learning techniques in the attribution methodology to improve it. And another student at Texas A&M, Sean Martinson, who's going to be part of the MTV project going forward at Texas A&M, is right now working with Argonne National Lab. So neither of these collaborations were something that existed before the March meeting. So it was really exciting and gratifying to see kind of how quickly MTV can accelerate this research by providing some really cool partnerships with national labs, ones that are, I wouldn't have thought to go to machine learning because I'm not somebody who does machine learning, but we were approached by Lawrence Livermore, and it makes a lot of sense with the problem that we have of having this data set and maybe finding better ways to use it. So with that, some next steps, we're going to continue doing this sensitivity analysis of selected isotopic ratio groups and implement like a tiered approach or a flow to how those groups interact. We're also trying to expand which isotopic ratios we can use via PureX process modeling. I believe that's what Sean's working on this summer. And then the machine learning stuff that we talked about. Additionally, we want to perform some validation experiments. So that'll be exciting for Sean and I. I mostly do computer stuff, so it'll be fun to get back in the lab again. So yeah, so that's what we've got going forward, and I just wanted to thank the consortium, both the administration and all of the research partners within it. Wanted to thank the national lab collaborators that we've begun to develop, and then I would also like to thank the sponsors, NNSA and DOE, for their continued support. So with that, hopefully I've got some questions to answer.
All right, Patrick, thank you very much. That was a very nice talk. Any questions from the audience that people would like to ask Patrick? Well, while the audience might be thinking about questions, let me pose one for you. Could you move back to your slide number 6, let's say?
Sure.
Okay. Now go forward a couple more. I want to look at the isotopes that you're using. Okay, that one's fine. But if you go a little further, you notice you looked at samarium ratios.
Yes.
If you go a little bit further than that, now, where is the physics that says the samarium ratio should be different for a thermal reactor? Because the first two are thermal reactors and the third is a fast breeder, right? So I
Yes.
expect the spectrum to be different. How is that reflected in the ratio of the isotope activities?
How are the samarium, how are the differences between the AP1000 and the PHWR? How are those probability distributions so different? Is that what you're asking?
Well, pick the middle chart. Tell me why the physics supports the pressurized heavy water reactor having a higher ratio than a fast breeder reactor.
You know, it's been a while since I've taken a reactor physics class. And I also didn't pick these ratios because, you know, this is a methodology that I've inherited. So I don't have a great answer for you right now.
Okay,
but
think about the physics, though, of why a spectrum, for instance, I presume it's these ratios are produced from wherever they're produced from fission, their fission products,
yes.
and why those ratios are different for the different spectral reactors. That may help you understand a value of one set of isotopic ratios to another associated with whatever property you're trying to uncover. See what I'm saying?
Yes.
Okay.
I mean,
All righty. I just think I think there's physics in there that might help you pick those ratios in trying to, because what you're really doing is trying to do diagnostics.
yeah.
And the physics might, if you know the physics ahead of time, you might be able to pick which reactions and which ratios are going to give you the most information for the question you want answered.
Yeah.
Anybody from the audience think that makes sense?
I want to add here, this is Sunil from Texas A&M. So for example, I think Patrick might have forgotten, we had this discussion a few months back. So in a thermal reactor, samarium-149, we know that is a fission product and a neutron poison. Once that is produced, samarium-149, in a thermal reactor, that absorbs neutrons and then that get converted to samarium-150. In a fast reactor, that is relatively less likely to happen. And compared to the PHWR and the AP1000, one specific assembly that he has picked here, there are spectral differences there too. So that's what it is resulting in this type of graph. The spectral difference, as Dr. Vehi correctly pointed out, the FUN49 production results in samarium-150 because of the higher absorption of samarium-149 into producing samarium-150. So these isotope ratios were selected from that perspective. So samarium-149 to 150 is a very good marker to differentiate between a thermal and fast spectrum. That is for sure. And then there are in between spectral differences for PWR, pressurized water reactor, BWR, boiling water reactor. These are small spectral differences depending on which part of the reactor you're taking this sample from. So that's what it is resulting. And this is true also for Pu-240 to Pu-239. The same phenomena of Pu-239 absorbing neutrons becoming Pu-240 preferentially more in a thermal reactor compared to a fast reactor.
Got it. Okay, that's very interesting. I think I understand a little more now why those particular reactions were chosen. One more question, if you wouldn't mind, Patrick. You mentioned something about a student doing work with argon on the Purex process.
Yes.
How would the reprocessing, the Purex process, affect the isotope ratios?
So the primary motivation behind the industrial PRX modeling is right now we're limited to only intra-isotope ratios because we don't have an understanding of the decontamination factors for each of the isotopes that will exist within the separated plutonium sample and be of interest to us. So if we are able to, accurately quantify those decontamination factors, then that might allow us to use isotopic ratios that are not intra-isotopic. We could compare isotopes of different elements because we have an understanding of, depending on certain parameters within the PRX process, industrial PRX process that was used to produce this separated sample, then we could have an understanding of the decontamination factors that would allow us to maybe expand, the different tools that we use in this methodology of different ratios.
Okay.
So that's the motivation behind that. So we're hoping that.
Let me add a couple of things very quickly. So all the ratios that Patrick showed here are intra-element isotope ratios, same element ratios.
Yeah.
We chose that because the PRX will not affect the same element, decontamination factor. But if we can understand better thermodynamics and the kinematics of how fission products move within the PRX process, then that will be helpful for us to get more ratios than the intra-elemental ratios. And that's what Sean is trying to work with Argonne. They have a good PRX modeling capability there to understand both thermodynamically and kinematically how decontamination happens for each of these different elements. So that's that work.
I would wonder if that isn't already known. I mean, the people who do these studies, and I'm sure you're talking to the Los Alamos people, they would know this pretty well. If that isn't pretty well understood, the efficiency of flow through of various isotopes through the process, not isotopes, elements through the process.
Yeah, so the elements are very well understood. Only thing, we don't have grip on the code that is used. So we would like to use those codes that exist with Argonne National Lab, input our experimental parameters that we use, the settling time, time to stir, how much molarity, all those, and then try to use our experimental data to produce that database. So there is knowledge out there about how these things vary, but our experimental conditions, we need to fit into that model.
Yeah, I think the labs could really help you out a lot with this.
Yep.
Good. All right. Well, any other last questions before we move on to our next speaker? If not, Patrick, if you wouldn't mind releasing your screen.